Okay, now we're going to look at how to actually solve a system of two linear equations, two unknowns, so that we can get to the exact point where they intersect or the solution. Two methods. The first one we'll look at is substitution. Here's the steps, and I'll go through them quickly, but then we'll do a couple of examples and it'll become pretty obvious what they are. First thing you want to do is you'll have two equations. Pick either equation and solve it for one of the variables. So in other words, set it equal to x or y. Okay, so let's assume you did it for x. So you'll have x equals something and there'll be y's over there. What you want to do then is take x out of the other equation and substitute that value for x in there, which will include a y. So when you do this substitution at this point, then you will have all one variable. When you have an equation with one variable, you can solve it. So you're going to get a number. Take that number, once you solve it, substitute it into either one of the equations and go back to the original equation. If you make any modifications, that's your best bet. Anyways, put that number in there, then that will give you an equation with the other variable. Solve that, and then you'll have your values for each variable. And then finally, you'll wind up with something like, say, x equals 5, y equals 2, that kind of thing. But you want to write your answer in this format, so that's a point. Okay, so let's try it. Okay, here we go. Here's a system, two equations, two unknowns. I got to solve one of these for x or y. It doesn't matter which one, but this one looks the easiest, and that's generally the way you want to go. Makes less work. So if I move y over here and I subtract 2 from both sides, I'll wind up with this. So that's pretty easy to solve for y. Okay, so we've solved one of the equations. Now step 2, in the other equation, which then would be this one, I want to substitute this value right here for y. So I have 2x plus 5 times y, and y is the same as this. Okay, I can solve this for x. So move the 10 over here, add these two together. If I divide both sides by 42, x equals, this reduces to 1/2. Okay, so we've solved for the variable after we substituted in. Now substitute this number for x into either one of the equations. And this is where I was talking about original equation. You can substitute it into this, or this, because these are the same equation, just solved differently. But the idea of going back to the original is, if I made a mistake here, then I might pick it up. So we want to go back to the original so we have our best shot at getting a value for y. So I can put that into either one of these. They really both look just as easy as the other. I'm going to go ahead and choose this one, but again, it doesn't matter. So 8 times x, now, which we know is 1/2, minus y equals 2. Half of 8 is 4. So y has to be 2. 4 minus 2 equals 2. So y equals 2. So these are my numbers, and then to write the solution, I want to do this. So the solution is the point 1/2, 2. All right, let's look at one more. This is a good example because when you're dealing with fractions or decimal points in this case, a lot of times it's a good idea to get rid of them or clear them before you really get going. So what I would like to do is rewrite this system, and what I want to do is this. If I multiplied everything by 10, I would be moving the decimal over 1 in each of these cases, and I would just have regular numbers here. So I'm going to do that. So the decimal moves over one place in every term. Same thing down here. So 5y minus 15. And then don't forget, on a regular number, there's a decimal there, so you want to move that over also. I'm going to go ahead and consider these originals. So I've changed the system to look like that, but they're actually the same equations. Okay, so I want to solve one of these. Again, this one's almost completely solved for y, so why don't I just finish that? And if I went here, if I divide everything by 5, y equals minus 15 divided by 5 minus 3, and 20 divided by 5 is 4. So I'm going to substitute that into this original here for y. So 12x plus 4 times y, which is the same as this, equals 50. So 12x, distributive rule here. So let me change that then, because that's going to become a plus times a minus. That's minus. 4 times 4 is 16. Okay, 12x minus 12x, they actually cancel out. And what am I getting here? This is impossible. 16 can never equal 50, so what does that mean? We can never have a solution. So that means we have no solution for this system. So what does that mean as far as describing the system goes? It's inconsistent. And if we wanted to go one step further, since there's no solution, that means I have two parallel lines that never cross, so that's still two lines. So this is inconsistent, but independent. I have two independent lines. Okay, so there's an example of each. Let's move on to the now the next method and see how we can solve systems using this next method. By the way, let me get set up here. Okay, by the way, either method is good. Generally what you want to do, it's either personal preference, or you look at the system and decide which method would be the easiest to use. But again, you could use just one method or the other, it doesn't matter. Okay, this is called the elimination method in the book, but I've seen it referred to as the addition method, which makes more sense. Basically, what you want to do here, rewrite each equation in the standard form, ax plus by equals c. So you're going to have ax plus by equals c, then you're going to have another one right underneath it. And then what you want to do in step 2 is multiply one or both of the equations so that when you add the two, and that'll be in section 3, part 3 here, when you add the two equations together, one of the variables drops out. So what you're looking for is additive inverses. So for example, if I had a 5a there, 5x there, and an x here, I might multiply by minus 5 here. So 5x minus 5x, they cancel. We'll see that in a minute. So once you add them up, one of the variables is going to drop out. That means you'll have an equation with one variable, solve it, take that number, substitute it into either one of the originals, and solve for the other variable. And again, report your answer like this. Okay, so let's try it. ax plus by equals c. We're done here. This one's all set. So let's just rewrite it. This one I need to rewrite in this format. So I need the x term first. Oh, it's already written that way. Okay, we're good to go. But what I want to do here is this. This is why I wanted to rewrite it. It's good to go, but I'd like to get rid of this fraction. So what I'm going to do on this one is I'm going to multiply everything by 3. So I'm going to put 3x, and then the 3 would cancel here, so I'd have minus 2y. And then finally 3 times minus 4, minus 12. So I could start here, they're in the order, but I don't like working with fractions, so I'm clearing the fraction. Again, personal preference. Okay, I got two choices here. Remember, the goal is either have the x's cancel out or the y's. I could have minus 15 and plus 15 here, so I could multiply this one by 5 and this by 3. Or I could go here and I could use minus 6 and plus 6. Again, personal preference, doesn't matter. I like smaller numbers, so I'm going to go ahead and do it here. So what you're doing is this. I'm multiplying this entire equation by 2 because I want a 6 here. I'm going to multiply this entire equation by 3 because I want a minus 6 here. That way the y's will cancel. So let's do that. So minus 5 times 2, minus 10x, 2 times 3 plus 6y, 2 times 9 is 18. 3 times 3, 9x, 2 times 3, and it's a negative, so that's minus 6y, equals minus 12 times 3, minus 36. Okay, so we've written them in the standard form, which they already were, but we went ahead and got rid of the fraction. We multiplied one or both. In this case, we had to multiply both so that we could get one of the variables to cancel, which is here. Now we're going to add the equations together. Minus 10 plus 9, that's minus x. These cancel, equals minus 18. Divide both sides or multiply both sides by a minus 2, and x equals 18. Okay, go back to either one of the originals, okay, and put 18 in for x and see what you get. I'm going to use this one because 3 divides into 18, so that's going to be nice. Or, I'm sorry, forget that. I'm putting it in for x. So this one might be better, or I could use this one right here. That's actually still the original, just rewritten without fractions. So let me use that one. So 3 times x, 3 times 8 minus 2y equals minus 12. Okay, so this is 54. And I'm going to add 12 here. And I'm going to add 2y over to that side. So I can get, I want to solve for y. This would be 66. Divide both sides by 2. Y equals 33, so our solution is the point 1833. And again, if you want to check any of these solutions, you would plug that into the first one and make sure it's true. You would plug it into the second one and also make sure it's true. Both have to be true or it's not a solution. Okay, let's look at one more. Let's use the addition method here. And, okay, no fractions, no decimals. So take a look at this. What do we want to do here? Well, could do a lot of things. I'm thinking of just looking at the p's here. And since I have 3 and 4, I could make this a 12 by multiplying by 4. And I can make that a minus 12 by multiplying by negative 3. Then those p's would cancel. So let's try that. So I'm going to multiply the top one by 4. And I'm going to multiply the bottom one by minus 3. Now, could I have used minus 4 and plus 3? Sure, it doesn't matter. Okay, this is just the way I chose to do it. You're trying to make things simple. So for example here, I probably wouldn't try and eliminate those because I'm getting into some pretty big numbers to try and make this work. So you have to look at it and figure out what you want to do. So let's multiply this out. So 12 minus 24p, and finally that's going to be minus 60. Down here, minus 12, that's what we want. Here I have a plus 24, and here I have a plus 60. Add them up. What do we get? Cancels, cancels, cancels. So what do I have here? 0 equals 0. Now this is interesting. 0 equals 0 is always true. It doesn't matter about P and Q. You're always going to get true thing here. So what does that mean? That means no matter what P and Q are, I have a solution. So what I have here are 2 lines on top of each other. So when you get a true statement and there's no variables there, that means infinite solutions. What does that say about the system? It means it's consistent. Okay, it's consistent because we have one or more solutions. Okay, but it's dependent because I only have one line. Each line depends on the other. So in the previous example, let me go back to that. We had a solution where it could never be equal, and notice again, no variables. So if you get an impossible situation, that means no solution. Inconsistent means no solutions, and then independent because the lines never cross, so you have to have two lines. And then again, let's compare that to this one. In this case, it's a true statement. The variables aren't there, so it's always going to be true. Nothing can change it. That means anything's a solution on those lines. That means infinite solutions. When you have infinite solutions, again, that's consistent because that means one or more solutions. When you have infinite solutions, that means every point on one line is a point on the other line. That means the same line. That means dependent system. Okay, next time we'll wrap up this in the final part, and what we'll do is we'll just apply this to a couple of application problems or word problems.